So we have our data that we're working with is the heights for men. So heights of men are approximately normal with a mean of 70 and a standard deviation of 2.3. On the next page, we have a function that's going to allow us to select three random heights from a theoretical model. And our calculator is actually going to allow us to do this over and over again so we can keep getting a new random sample of three heights. And then our calculator in the spreadsheet, we're going to get the z-score, and we're going to look to see how often the z-score is below -2 or more than +2. So I did a random seed, and my first sample has these three heights with a z-score of this. So that's definitely something that's between -2 and +2. So if I do this a couple times, I have one that was outside. A lot of these are, I've only so far had one, two. Okay, so let's see how this is looking. So this made a dot plot of my sample means. So each one of these was one of the X bars that we calculated in the last page. And what you're going to notice is most of my values are between -2 and +2. I have a few that are beyond, but the majority of them are between those two values. Okay. And if I wanted to, I could look at it as a histogram instead of a dot plot. Now, the problem is in real life, we don't usually know the population standard deviation. So back when we were talking about distributions of sample means, we were using a model. If we were talking about something that came from a normal distribution, where this is doing an arrow instead of a line. We're centered at the mean, and our standard deviation was the population standard deviation over the square root of the sample size. If we were going to calculate a z-score, it was our sample average minus the population mean over the standard deviation of the population over the square root of the size of the sample. However, what we tend to run into is if we really knew what the population standard deviation was, then we'd be knowing a lot more about the population, but we usually don't. So we end up having to use something called a t-distribution. So we are going to be using a t-distribution now because we usually don't actually know the population standard deviation. So this is what we use, and we calculate a t-score. So you're going to see it's pretty much the same, but it uses this S. S is for the standard deviation of the sample, which we should know because we collected the sample. Okay. So now we're going to be able to do the same thing, but we'll be able to do this using a t-score. So here's the heights that I'm going to collect again, and my t-score formula is pretty similar to my z-score. It just uses the population, the sample standard deviation instead. So I'm going to do this a couple times. And you're going to notice like, whoa, that's a bigger t-score. Got another one. And another one that was -4. This one's positive, almost +6. So I'm going to do this a few more times to get a few more samples. I've definitely gotten a few that's like pretty big compared to what we're used to getting for z-scores. So when you look at this distribution, there's a couple things that you're going to notice about this model. So the first thing that you should notice, which sometimes people call this the student Model T, this has a lot longer tails than our normal distribution, okay? And when we did our simulation, these scores are stretching like almost as far as -6. And we can get even larger ones. So, what you need to think about is if we like increased our size of our sample, maybe if we looked at more than 3 heights, we could look at 25 people and take the average of their heights. So this is a list of 25. So I'm going to do it just one more time. And if you're looking at these numbers, they're not quite as big. So now, if you take a look at this, this is much more compact. So as my size of my sample got larger, there's less variation. So my distribution of t-scores is getting closer together. Okay, so as the size of our sample increases, this is actually going to get closer and closer to looking approximately normal. Okay. And this kind of has like a picture for you to see as we take the size of our sample and make it larger and larger, this is going to look closer and closer to a normal distribution. So the red here is a normal distribution, and the blue is a t distribution. So what we're going to do is we're going to change the size of the sample. So what's important to know is the size of the sample. We have a little bit of vocab that goes with that. So we still use n for the size of the sample. And then our degrees of freedom I'm going to fix my calculator. The Zoom went crazy. Our degrees of freedom is going to be the size of our sample minus 1. Okay? And basically, our distribution, our t distribution, the blue here, is going to fluctuate depending on the size of our sample. So here we have like a little arrow that's going to let me swap around the size of the sample. So turn this off. If we increase the degrees of freedom, so now it says sample size of 3, 4, 5. If I keep going, you're going to notice that this keeps stretching up to almost look like a normal distribution. Okay, the larger and larger it gets, the closer you can see that it's like superimposed on top of a normal distribution, and the tails are getting smaller and smaller on the ends. They're getting closer to the x-axis here. That is because there's going to be less variability from one sample to the next. So if I decrease the size of the sample, so degrees of freedom is 1, there's only 2 in my sample, there's more room under the tails here. Okay. The next video you're going to watch is actually going to give you like the story behind how the student Model T was invented.